right, so we're going to be looking at Unit 3, Notes number 6. And for Unit 3, we're still looking at all different types of functions, but now we're going to be looking at how can we actually represent those functions in a little bit different way. So today the goal is I will be able to identify different types of sequences. Oops. So that's going to be our goal today. Okay, so looking at the first one, where sequences are all about patterns, just like functions are about patterns. We're either adding or we're subtracting, we're multiplying by a fraction, or we're looking at those second differences for quadratic. So functions are all about patterns, and sequences are also all about patterns. So if I look at number 1, I have -5, -1, 3, and 7. I'm looking for the pattern here. So how did I get from -1 or -5 to -1? Well, I'm adding 4. 1 to -1 to 3, I'm adding 4, and 3 to 7, I'm adding 4. If you can remember from the last video, the last set of notes, we said anytime we're adding, that is going to be a linear function. So what type of function? Linear. Now there's a specific type of sequence that goes with that. So anytime we're talking about a linear function, the sequence type is going to be arithmetic. Arithmetic. It's a fun word to say. Arithmetic. Okay, so we're adding arithmetic. Anytime we add or subtract, it's going to be arithmetic. So why don't you write that off to the side? Add or subtract. So whenever we're adding or subtracting, what we're adding or subtracting by is going to be called our common difference. And for this one, our common difference was +4. All right. Okay, so anytime we see a linear function, we know that arithmetic is going to go with it. Now looking at the next one, maybe, there we go. To go from 2 to 6, it looks like we're adding 4, but to go from 6 to 18, I'm not adding 4 anymore. Okay, so that pattern's not going to work. Okay, so adding 4 didn't work. So how else can I get from 2 to 3? Well, the other way to get from 2 to 3 is if I multiply by 3. I said 2 to 3. I meant 2 to 6, my bad. So how can I get from 2 to 6? I can multiply by 3. 6 to 18, I can multiply by 3, and 18 to 54, I can multiply by 3. So we see that we are multiplying by 3 in our pattern. Okay, so anytime we're multiplying, if you can think back to our last set of notes, notes number 5, anytime we said we were multiplying, that type of function is going to be exponential. And the specific type of sequence that goes with exponential is called geometric. Now, since we're multiplying by 3, what we're multiplying by, that's called our common ratio. And what was our common ratio? Well, we were multiplying by 3. Okay, so ratios go with geometric, differences go with arithmetic. All right, so how can we represent these sequences? Well, just like with a function, we can graph it. We can also graph a sequence, okay? Very, very similar. So first we need to identify the sequence and the function type, just like we've been doing. So if I look at this, to go from 15 to 12, I'm subtracting 3. 12 to 9, I'm subtracting 3. 9 to 6, I'm subtracting 3. I was subtracting each time. Okay, so if we look up here, we said anytime we add or subtract, that's going to be arithmetic. Give you a little hint, guys. Anytime we see A sub n in the table, guess what? A stands for arithmetic, okay? And if it's in a table, I have to label it correctly. So you can always look at that and I'll say A sub n. So guess what? You know right off the bat it's going to be arithmetic. And then, so what type of function goes with arithmetic? Linear. All right. So now we're going to set up our graph. The very first thing we always do when we set up a graph is label. Okay, so we have n right here. So that's going to go on our x-axis. Okay, so we have 1, so 0, 1, 2, 3, and 4. Make sure you space them out so you have enough room. And then for our scale on the y-axis, we know it's going to be a sub n. Oops. And since our difference was 3, I'm going to go up by 3s. It's going to be the easiest to plot the points if you go up by 3s. I might have been able to get away with skipping, but that's okay. Yes, you have to take your scale all the way to the end. Don't be lazy. All right, so my first term was 15. My second term was 12. So 2 up to 12. My third term was 9. And my fourth term was 6. Okay, and then I want everybody to write off to the side. Do not connect the points. Or don't connect points. The reason you don't connect the points is because these are individual terms, not a function. They are individual pieces. So we don't connect the points because then it'll include all the things in between. Okay, and we only want the individual pieces. All right, flipping the page over to the back. Looking at number 4, same thing. We're just going to be graphing this. Guys, give you a hint. There's a G right here, so we know it's going to be geometric. That means our pattern should be multiplying. We should be multiplying by something. Well, what can I multiply 16 by to get to 8? Geometric means I have to multiply, so it's getting smaller. Anytime my numbers are getting smaller, then I'm actually going to multiply by a fraction. So 16 to get to 8, we're going to multiply by 1/2. 8 to 4, 1/2, and 4 to 2, 1/2. Okay, so I'm multiplying by 1/2 each time. Okay, oh, I forgot. What type of function goes with geometric? Exponential. Sorry, guys. So now I need to go over here and label my graph. N always goes on the x-axis. 1, 2, 3, 4. And then we're going to label our x-axis. I'm just going to go up by 2s. 2. Yes, you need to go all the way to the end. Again, don't be lazy. So our first term was 16. The second term was 8. Oops. The third term was 4, and the fourth term was 2. All right, and then remember, we do not connect our dots. All righty. Just going to keep on going on some of these problems. Looking at number 5, we have 192, 96, 48, and 24. So my numbers are getting smaller, so that means I either have to be subtracting or I'm multiplying by a fraction. Those are my only options. To go from 192 to 96, I'm subtracting 96. But if I subtract 96, that does not take me to 48. So I know, hey, that's not my pattern I'm looking for. So since that's not the pattern, that means I have to be multiplying by something. Okay, well remember, to get smaller, we're multiplying by a fraction. Well, half of 92 is 96. So we're multiplying by 1/2. Half of 96 is 48. So we're multiplying by 1/2. And then half of 48 is 24. So we're multiplying by 1/2. Anytime we're multiplying, okay, and that's our pattern, the function type is going to be exponential. And then the sequence type, the sequence that goes with exponential is always going to be geometric. Now, since I am multiplying, okay, that is a common ratio. And if I look at my pattern, the common ratio was 1/2. Alrighty. Next one, number 6. We have 11, 6, 1, and -4. So again, our numbers are getting smaller. That means we either need to be subtracting or multiplying by a fraction. So to go from 11 to 6, we're subtracting 5. 6 to 1, we're also subtracting 5. And 1 to -4, we're subtracting 5. Since I'm subtracting by the same number, my function is going to be linear. But this isn't a function, we're talking about the sequence type. So the sequence type that goes with linear is arithmetic. Now, since it is arithmetic, we're subtracting. That means we're going to have a common difference. And our common difference is we're subtracting 5, so -5. Alrighty, last one, number 7. It says determine whether each of the following is linear, quadratic, or exponential, or none. Okay, so we're just going to go through a few of these. We probably won't get through all of them, and that's okay. So the thing with this is that you always have to simplify first. So step 1, simplify first. And then we have to always look at our exponents. So for linear, that means the largest exponent is going to be a 1. Quadratic, the largest exponent is going to be a 2. And exponential, my exponent is always going to be an x. So always look at the exponents. So if it's a 1, it's linear, 2, quadratic, or if it's an x, it's exponential. And if it's none of those, then guess what? It's none. So if I look at the first one, I have a y equals 7x times x minus 3. Remember, you have to simplify first. So I need to distribute that 7x to everything. When I do that, I'll have y equals 7x times x gives me 7x squared. Wow, that was an awful 7. 7x squared. Then 7x times -3 gives me -21x. So now this is simplified. And if I look at this, the largest exponent here is a 2. Therefore, this has to be quadratic. The next one, I have a y equals 7x minus 5. If I look at this, the largest, it doesn't look like there's an exponent, but there's actually one here with the x. Okay, and anytime our exponent is a 1, we said it is linear. On the next one, if we look at this, we have x and y together. They're being multiplied together. Anytime you see the variables being multiplied together like this, the x and the y, it's going to be none. If I look at the next one, I have y equals 2 divided by x. Anytime the x is in the denominator, that's also going to be none. And then the next one, I have f of x equals 5 to the x power. Anytime we set our exponent as an x, that's going to be exponential. All right, we're going to go ahead and stop there. Okay, we're not going to worry about the last row. If you have any questions about those, please make sure you're asking. Okay, if not, you can move on to your assignment.